Hello everyone. My name is Dr. H.S. Madhusudan, Assistant Professor of Mathematics. This is a BSc program of University of Mysore. Paper 5. Title of the paper is Real Analysis 2 and Algebra 3. And this is unit number 3. Here we study rings and fields. In the previous session, we understood the definition of rings with examples. Now let us study some properties of rings. So first property, in a ring R plus into, for all A belongs to R, A into 0 is equal to 0 into A, which is equal to 0, where 0 is the additive identity. What? A into 0 is equal to 0? It is quite obvious. We are writing this for a long time. 7 into 0 is equal to 0. 3 into 0 is equal to 0. What is there in it to prove? Exists a proof? Yes, we can prove. Previously it was not possible, as we didn't have the knowledge of rings, but now we know the definition of rings, and using only rings we can prove this. Okay, let us see how. See, there are two collections. Each collection contains 3 objects. Means what? 3 into 2, which is equal to 6. But what is 3 into 0 equal to? 3 objects in a collection, but 0 collection. It looks quite obvious, which is 0. But how to prove it? Let us prove it. Now, A into 0 can be written as A into 0 plus 0. But 0 can be written as 0 plus 0. See, from we know rings, the definition of ring, and the identity element, the property of identity element. A plus 0 is equal to A, and this is true for all A belongs to R. So that is the property of identity. Now since 0 belongs to R, we can replace this A by 0, and then this A becomes 0. So therefore 0 is equal to 0 plus 0. So therefore this A into 0 is equal to A into 0 plus 0 can be written as A into 0, which is equal to A into 0 plus A into 0 by distributive property of R. Right? Now what is A into 0? We don't know. We have to prove it. A into 0 is equal to 0. So consider A into 0 is some element belonging to R. Since A belongs to R, 0 belongs to R, and R is closed under multiplication, A into 0 is an element of R. Let us call it as X. So X is equal to X plus X. In R, inverse of X under addition exists, and that is nothing but minus X. So add both sides by minus X. So now use on the right hand side, use associative property to combine this minus X with this X. So when we combine X with its additive inverse, what we get? We get 0. So therefore we have 0 is equal to 0 plus X. Now using the property of identity element, 0 plus X can be written as X. So therefore X is equal to 0. But what is X? X is nothing but A into 0, which is equal to 0. Wow, we proved. Before proving, it was looking so obvious. Now it needs a proof. So we proved it. Now let us see the second property, which states in a ring R, for all AB belongs to R, A into minus B is equal to minus A into B, which is equal to minus AB. This is also quite obvious. We are using it for a long time. 3 into minus 7 is minus 21. Minus 3 into 2 is minus 6. Again, using rings, we can prove this. See how. Consider AB plus A into minus B. Now in a ring R, distributive property holds, so we can take that A as common factor and we can write this as A into B plus of minus B. Now B plus of minus B is 0, so A into 0. But now, just now we proved A into 0 is equal to 0. Now what it tells? AB plus A into minus B is equal to 0 means inverse of AB is A into minus B. See, if A plus B is equal to 0, that means what? B is the inverse of A or A is the inverse of B. So we write A inverse is equal to B. Therefore, AB inverse is equal to A into minus B. But actually, what is the inverse of AB under addition? It is nothing but minus of AB. Now the left hand sides are equal and therefore these two right hand sides must be equal. So therefore A into minus B must be equal to minus AB. Similarly, we can prove that minus of A into B is equal to minus AB. Right? Okay. Here comes the next property, which states in a ring R, for all AB belongs to R, minus A into minus B is equal to AB. Okay? Now, consider minus A into minus B, which can be written as minus A into X. What is X? X is minus B. Now, from the previous property, minus A into X can be written as minus AX. Now replace X by minus B. Now again apply the previous property, that is A into minus B is minus AB. So we get what? Minus of minus AB. Now X inverse under addition is what? Minus X. So therefore, what is the inverse of minus X? Which is minus of minus X. But actually inverse of minus X is X. So therefore X is equal to minus of minus X. And hence we get AB. So therefore we proved minus A into minus B is equal to AB. Now, next property states is A into B minus C is equal to AB minus AC for all ABC belongs to R, where R is a ring, and B minus C into A is equal to BA minus CA for all ABC belongs to R. So again, how to prove this? Consider A into B minus C. Now this A into B minus C can be written as A into B plus of minus C. Now use the distributive property. It states A into B plus C is equal to AB plus AC. So what do we get? AB plus A minus C. But a into minus b is what? Minus ab. So therefore, a into minus c can be replaced by minus ac. So we get ab minus ac. So therefore, a into b minus c is equal to ab minus ac. Similarly, we can show that b minus c into a is equal to ba minus ca. Right? Okay, next property. In a ring R plus into with unit element 1, minus 1 into a is equal to a into minus 1, which is equal to minus a. And this is true for all a belongs to R, and minus 1 into minus 1 is equal to 1. The second one is very easy, because we just proved minus a into minus b is equal to a into b, and since 1 belongs to R, in place of a and b take 1, we get the result. To prove first one, we have this property minus a into b is equal to a into minus b, which is equal to minus a into b. So by appropriate substitutions, we prove first one. Here comes the next one. If R under addition and multiplication is a ring with identity in which xy whole square is equal to x square y square for all xy belongs to R, then R is a commutative ring. That is, x into y is equal to y into x for all xy belongs to R holds. So that is what we have to prove. See, this one is looking very simple, because x square can be written as x into x, and therefore xy whole square can be written as xy into xy. Now the left hand side is xy into xy and the right hand side is x square into y square, which can be written as x into x, y into y. Now using left cancellation law, we can cancel out x, and by using right cancellation law, we can cancel out y. So remaining thing is what? Yx is equal to xy. Quite simple. Wait a minute. We have not yet proved cancellation laws under multiplication holds in a ring. So this is not the way to prove it. See, cancellation law under multiplication holds in integral domains, which we study in later sessions. So then how to prove this? Please stop watching this video for a while. Think about this problem. Try to work it out. If you get the result, very good. If you don't, then see the video for the proof, and look at the way we prove this. So elegant. You will definitely enjoy it. Okay, have you tried? Now let us see the proof. Now given xy whole square is equal to x square into y square for all xy belongs to R. Now 1 belongs to R. Therefore R is closed under addition, and hence x plus 1 comma y plus 1 belongs to R. So in this expression, replace y by y plus 1. See, this condition holds for all xy means it holds for y plus 1 also. Now how to expand y plus 1 whole square? For this, let us expand a plus b whole square in R, which will be equal to a plus b into a plus b. and that will be equal to A into A means A square plus A into B plus B into A plus B into B, which is B square. Now I cannot write BA as AB because commutative property doesn't hold. We have to prove that. So whenever you write BA, it is only BA. Now using this property, you can expand. Say on the left hand side we have what? X into y plus x whole square. On the right hand side we have x square into y square plus y plus y plus 1. Right? Now expand xy plus x whole square similarly, and we get this result. Now xy whole square means what? Given x square into y square. So the first term xy whole square can be replaced by what? X square y square. Now x square y square and x square y square can be cancelled under addition, not under multiplication. So x square into y square and x square y square can be cancelled because its inverse exists in R under addition. Next, this x square y and x square y can be cancelled, and lastly x square and x square can be cancelled. So remaining thing is what? X y x on the left hand side and x square y on the right hand side. So x y x is equal to x square y. Now we have x y x is equal to x square y. Now replace here x by x plus 1. What do we get? We get x plus 1 into y into x plus 1, and on the right hand side we have x plus 1 whole square into y. Now expand it. We get this result. Note here the first term contains xyx, but now we have proved that xyx is equal to x square y. So therefore this xyx can be replaced by x square y. So now this x square y and this x square y can be cancelled, and then this xy and xy can be cancelled, and yy can be cancelled. So remaining thing is yx is equal to xy. We proved. Look at the way we proved this using only the definition of a ring. It is so elegant, so beautiful. Okay, I will end this session here. Thank you.